time we talked about duality transformation, I just showed you how a dual superconductor picture can lead to a linear potential which can lead to confinement. And I just want to say a couple of words more about it before I get into trying to do some calculations. This we did. So for example, for SU2 gauge theory, if you look at the charges or the charged particles, say imagine SU2 is broken to U1, you look at the W plus minus, the charges, it's easy to convince yourself, lie on a one-dimensional lattice that comes from the Dirac quantization condition. Okay. More generally, charges will lie on a lattice of dimension which is equal to the rank of the gauge group, and by analyzing the nature of the lattice, one can see what kind of dual group would apply to the dual magnetic based description of the theory. And this was done by Goddard, Knights and Olive, basically showing that this lattice of magnetic charges would be in the lattice terminology, the reciprocal lattice of the lattice of weights or charges for the given theory. Okay. So there is this correspondence between the group and the dual group that they establish, but beyond that it's not easy to do very much because we are not talking of configuration. We are only talking of configurations. We are not talking about solutions or anything like that. Okay. So one might ask, is there some way to see how this dual superconductivity that I talked about here would be realized by condensation of monopoles? And the only example I know of that is the work of Seiberg and Witten, where they looked at n equal to 2 Yang-Mills theory. You have a potential that is of this form, and so we can see that there are vacuum defined with some non-zero expectation value for phi, and you can even construct a whole moduli space of the vacuum of the theory. If you take for SU2, for example, phi going like some parameter A times the generator sigma 3 by 2, then you can construct the duality transformation, the moduli space, and then by analyzing the singularity structure, by looking at monodromies around infinity, they were able to conclude that there has to be additional singularities because the monodromies all don't quite match up. So there are additional points inside the moduli space where monopoles become massless. Okay. Yeah.
This is super Yang-Mills.
So sorry, super Yang-Mills. Yeah. That n is the supersymmetric extension. Yeah. Okay. So because of supersymmetry, one can actually make some exact statements. That was a really good thing about it. They add a potential term, perturbation term, like a mass term for a chiral multiplet. If you think of the n equal to 2 as n equal to 1 gauge multiplet plus 1 chiral multiplet, then the chiral multiplet you give a mass. So that reduces the theory to n equal to 1. Then they can look at the exact superpotential near the point where the monopoles become massless. Exactness follows from the supersymmetry, and they realize that there is a dual Higgs mechanism. Okay. So that's an example of where one can actually see this happening in practice, so to speak. But other than that, I don't know of any case where this has been successfully implemented. Okay. So it's a very, very special case. So I'm going to go back to the whole question of the gauge orbit space, because whether you are talking of the theory or the dual theory, ultimately the analysis of the gauge orbit space is very similar. Okay. Because if you are going to exchange E and B, you are effectively talking of the same space, except that E square, which is a Laplacian, B square is a potential, change places, B square becomes a Laplacian, E square is now the potential. Okay. Other than that, not much changes. Therefore, analysis in terms of the gauge orbit space is what I will try to pursue. Okay. So to begin with, recall that in the two-dimensional case that I discussed in some detail, the 2+1 case, the complex structure was very crucial for the 2D space to be able to find a parametrization of gauge fields that I could then use to calculate various quantities. Okay. So something similar should happen here. And of course, since you want some kind of complex structure, the splitting the 4D theory into 3+1 is not the right thing to do. In 2 plus 1 that would work because you would be left with 2D space which I could make complex. So here the idea is to look at directly the 4-dimensional space and ask, is there a parametrization of gauge fields I can come up with which does the job? Okay. So I want to show it to you that one can do that. Okay. Please.
So I didn't quite understand. Why does the 2 plus 1 dimensional case differ from the 4 plus? Okay. Is it because of obstructions or something?
No, because my parametrization that made all these calculations possible depended crucially on having a complex structure on the space. So if I take a 2 plus 1 dimensional theory, I have to split off time and focus on the 2D space, so I do a Hamiltonian description. If you do a 4-dimensional theory, I take the whole 4D space. Instead of a Hamiltonian description, I am going to do a path integral.
Why can't you do the Hamiltonian?
Because the 3-dimensional space wouldn't give me a complex structure, right?
The dimensionality.
Because of the dimensionality. So that's the idea. Okay. So how do we do that? And to motivate this, I want to go over what I did in 2 plus 1, but from a group theory point of view for a second. I'm going to look at CP1, which is SU2 mod U1. So we can use a group element in SU2 to coordinatize the manifold CP1. Okay. With of course the identification, right translation by U1 should be identified with the original G. Then one can actually show that there is a similar parametrization to what I did in terms of the flat space. R plus and R minus are right translation operators on the group element. They act as covariant derivatives on CP1, and I can write the gauge potentials in this fashion. This is essentially the sphere extension of what I did in flat space. Okay. And it comes essentially from group theory, as the next argument I am going to show you will convince you that's the case. So I want to try this structure. So we want to pick a space which is a complex structure and which would be nice to have it as a group coset space. So the space I am going to pick is actually CP2. Okay.
So the CP1 discussion is a Sartori model.
Yeah,
It's not
yeah.
CP2
That's right.
is what you're ultimately.
I'm going to do CP2, but CP1 is useful for my 2 plus 1 discussion. You know, I presented results on the flat space, but I could equally well have presented it on a sphere using this. Okay. Okay. So then the idea, then we want to calculate the invariant measure. That's the idea. So let's talk about CP2. Now, in addition to having a complex structure, there are some nice features to CP2. One is of course that it's SU3 mod U2. So you can do many things simply using group theory, which is very useful. Of course, the metric is the Fubini-Studi metric, which if I now take a large R limit after scaling the coordinates like so, it basically looks like a flat space. Of course, it's not just R4 because there is still a residual of the complex structure, but so it doesn't have the full O4 rotational symmetry, but nevertheless, we can attempt to get to the flat space by taking large R if needed. Okay. There are other nice things about CP2. For example, there is a conjugation symmetry in CP2 that relates it to S4. So one may even be able to use that in some fashion. Okay.
You will do only pure angles.
I will so far only do pure angles because it's quite involved.
Also, the reason I ask is
Oh, you're
because
doing
you
a
have
fermions, yeah.
on CP2.
That's right. You can't put fermions on CP2. That's a negative point. However, if it comes to doing that, I think there is a standard spin C structure one could utilize. So one could do that. Okay. Okay. So let's use CP2, coordinatize it by an SU3 group element. Now, an SU3, I'm going to use a 3 by 3 matrix representation of SU3 for various arguments here. Write translations on the group element. I can write like this, which these are half of the Gell-Mann matrices. T1, T2, T3 is SU2, which is usually called isospin. T8 is the hypercharge. And then the remaining generators I combine into complex combinations, T4 plus minus IT5, T6 plus minus IT7. These will correspond to translation operators on CP2. These are the translations. Okay. This is the local isotropic group, which means frame rotations at a given point will happen using the U2 defined by SU2 and U1. Okay. So with that understanding, we can see what happens with functions and so on. So let's look at, say, for example, functions on CP2. How do I do that? CP2 is, remember, SU3 mod U2. So I can start with functions on SU3 and ensure that they are invariant under U2, so they qualify as functions living on the base space, so to speak. So which means that I can expand any function on CP2 in terms of these representation matrices of SU3, but the right state must be so chosen as to have invariance under this SU2 and U1. Okay. So those are the functions I would get, which I explain in this way, that the right state must have invariance under the U2, which is 1, 2, 3 and 8. Okay. So if I look at the representations of SU3 labeled by two indices P and Q, like corresponding to upper indices and lower, so to speak, it's like product of 3 stars and 3s. Then JW is essentially all 3s like this, equal number of 3s up and down. Okay. That is the state I need. Okay. So that will give me a complete set of functions on CP2. Okay. But now it's not functions we want vectors, and now we can easily see what vectors are, because as I mentioned, U2 is the local isotropic group of frame rotations. So vectors must transform as the vector representation of U2. Therefore, we can simply ask what are the possible ways to get that. Okay. They have to be doublets of SU2 and they must have non-zero hypercharge plus or minus 1. Okay. That's what we need. It turns out there are several such representations, actually 3 types. One set simply consists of taking functions as in this previous discussion here, and simply applying derivatives on them. Ri and Ri bar are the translations. But there are representations of this type, P plus 3 comma P and its conjugate, which also contain vectors when you look at the states on the right. Okay. So therefore, there are 3 types of quantities that we can construct. So the parametrization of a gauge field of a vector will be gradient of a function via this derivative plus this extra piece here, and likewise this will be the conjugate. Okay. Now it turns out that these representations are of the P plus 3 P type. You can obtain by applying Ri bar. Notice that this is Ri, but if you take the conjugate Ri bar, apply it on a state with all 3s, you can get this. What does this mean? There is an epsilon tensor here. It means that that extra piece is the divergence of a rank 2 tensor. That's what it is. Okay. So the general parametrization that we get is of this nature: gradient of a function, that's this one, and then an antisymmetric rank 2 tensor, because of the dimensionality, is simply proportional to epsilon. Therefore, it's just another, it's not quite a function, but something entity with no indices. I can write like this by taking the dual, and so it is of this form. Okay. So these are the 3 entities we need. It is essentially what I have given you is like the Hart's decomposition, but specialized to CP2. Okay. That's what happens. Now we can use the same trick I used earlier, namely think of this as coming from expansion around the origin of SLNC, these factors here, and you can therefore generalize it to this parametrization. Okay. So this is a parametrization that holds for vector fields on CP2. Okay. So
Here, in the 2 plus 1 T case, you only need the holomorphic.
that's right. That's because this term was absent. I just needed that. Okay. And so this is very similar to, this part is very similar to two-dimensional case. But this is the extra piece, which is obviously because there are additional degrees of freedom in the 4-dimensional case. The good thing though is that this will help us factor out gauge transformations exactly as in 2 dimensions. Okay, that's advantage. Yeah. Each I is 1, 2, I bar is 1, 2.
So then that's because you're on CP2 now.
That's
Also the space-time mu indices.
yeah. So the mu index is
Okay.
2 of the I type and 2 of the I bar type.
So these extra pieces are gauge invariant.
These are gauge invariant, exactly. Okay. So this is a complete. I mean, I'm going to write it in another way in a minute, but you will see that this allows me to factor out gauge transformations very easily. It homogenizes the action of gauge transformations. That's the important thing. Okay. So I can do this. I can rewrite it in slightly different way by taking the phi, the tensor I mentioned, and tacking on an M inverse and M, so I can write it like this, which seems a little more natural. You can easily see now that left transformations on M by a group element is a gauge transformation. Okay, so M goes to G. Some U times M is a gauge transformation. The AI in the middle is gauge invariant. Same with AI bar. So that's advantage. Okay. So I might notice at this point that this is not just only trivial type of gauge field, so to speak, because if I drop the AI bar, it's known that these two guys are sufficient to describe anti-self-dual instantons. So there are some non-trivial topological configurations also that we can describe using this. Okay. Now, in terms of the M's and the phi's, you can easily write down the gauge invariant combinations. M diagram, the phi with these pieces here and this. So we have, these are conjugates of each other. So there are 2 degrees of freedom here total. There is 1 here, which along with the gauge parameter gives you the 4 degrees of freedom that you need in 4 dimensions. Okay. So that's the story. And now we want to ask the question, can we calculate anything on the gauge orbit space? And the first thing to calculate, as in 2 dimensions, is the volume of the gauge orbit space, the volume element. Okay, so I look at the metric, which is defined by variations of A and A bar. Write it out. There's a lot of terms here. There is a term that involves delta M inverse and its conjugate. This is the term we had in 2D. There is a similar term arising from the phi part of this, and then a lot of mixing terms here. Okay. So if I combine this and write it in some formal matrix form as script M times these differentials here, then I can compare this metric with this metric over here, which is simply defined by the differentials, and you see that the two should be related by the determinant of this matrix in the middle. Okay, when you look at the volume element. Okay, so what we need to calculate then. So before I do that, let me then write the volume element. Therefore, in this fashion, square root of the determinant of M, we have to calculate still. As far as M is concerned, which is coming from these two guys, factoring out gauge transformations works exactly as in 2D. You get an SLNC group element. SLNC mod SUN coset space group volume element. These are the extra fields chi and chi dagger in 4D. This is the volume of the gauge group that I am going to drop. So the invariant measure is given by this quantity. Okay. So the whole problem again reduces to computation of a determinant. Okay. In 2D we could exactly calculate this determinant. In 4D it's not possible to do it exactly. Okay. But we can ask, what are the leading terms that arise when you do, if you calculate in terms of a derivative expansion, the lowest dimension terms would be the ones which would be most relevant for the infrared physics. That's what we want to concentrate on. So therefore, can we write down what those are? Okay. So we had to calculate the determinant. I'm going to write it in terms of some bosonic fields just for facility of calculation. So it's like computing the partition function of some other field theory made of fields B and B bar and C bar with some action. The S naught is just what this is here, and then there are some interaction terms. Okay, the fields C and C bar are scalars in the sense of having 0 hypercharge and they have no SU2 indices. B and B bar came from those rank 2 tensors, so they have hypercharge 2 and minus 2 here. So therefore, computing these determinants already is a little bit involved, these guys. So, okay. So, I'm going to show you what comes out of the calculation, but first let me just say a couple of words about how it is done. Recall that these derivatives here, these contain m's inside, because I think I said, yeah, the derivatives are of this form. Okay, these are covariant derivatives. I don't need the full blown A to get covariance under the gauge transformation for this. I can just use this part. So, in terms of those, these are covariant derivatives like that. However, if I just take the free part, then what we need is free propagator for scalars and for y equal to -2 on CP2. But that again is another reason why CP2 is nice. It's a group coset. You can exactly calculate these propagators. Okay. So, by combining some differential equation technology and some group theory technology, we can work out the exact propagator for CP2 for scalar functions, and this is for the rank 2 tensor. Okay. And S in this formula is the distance between 2 points, which I can write in terms of homogeneous coordinates like so. So, the coordinates I am using are the familiar ones, namely homogeneous ones. So, I take some Zi, identify like this, 4 complex numbers, that I can use that as a parametrization also. So, if I write in terms of that, S is like this. Okay. So, that is essentially the covariant notion for the distance between 2 points, okay, on CP2. So, once we have this, we can go on to calculate. Okay, you need a UV regularization. So, we do a covariant splitting, which is a bit of an involved mess, but nevertheless, you know, this is essentially the second point in this distance is replaced by another point which is shifted from this by some small amount. That's basically. So, it's essentially point splitting. You just have to do it in a way that respects the isometries of CP2. Okay. Finally, you also need a Wilson line because you need gauge covariance as well, okay, not just covariance on the manifold. Okay. So, we do that. This takes care of that. So, after all this, you can actually do the calculation. Okay. It's still a bit involved, but I am going to focus on the results and tell you what it is. Okay.
Sigma that you showed seem to have some scale invariance and scalings of these coordinates. That is inherited from CP2?
You are talking about this one? Yeah, indeed. That is because, to remember, these are my homogeneous coordinates on CP2. So, anything that lives actually on CP2 must have scale invariance. So, this is the distance as defined on the manifold CP2. So, indeed it should have the scale invariance. That is right. Okay. So, here is what we find, and this is where there is a bit of a surprise. So, we calculate this. I am going to take out this factor and look at the determinant, write it as e to the gamma. And what do we expect if you think in terms of terms involving various terms of various dimension? It will start with the dimension 2 term, then could be dimension 4, dimension higher than 4. These terms are potentially divergent from just power counting. Dimensions higher than 4 will be finite. Okay. So, we can write this down. We are going to calculate these 3 terms up to dimension 4 terms, and I am going to show you the result. The fact that there are infinities here means the measure needs to be renormalized in the theory. There is no surprise there, because what is in the measure? The usual Faddeev-Popov determinant is part of the measure, and we know that there is renormalization needed there. This is just, we are doing the same thing in invariant coordinates without gauge fixing, but that does not avoid the problem. You still need to define a renormalized measure. Okay. So, therefore, there is no surprise that there should be such divergent terms, but the surprise would be in the nature of what these are. So, I am going to talk about these 3 terms, starting with the dimension 4 and then coming down. Yeah.
In the 2+1 dimensional case, there was no divergence, right?
That is right, because remember the 2+1 dimensional theory is super renormalizable, right. So, I did not need that, but this is not. So, this is again some of the complications when you go to 4 dimensions, right.
So, this is ultimately also
Exactly, exactly. That's the point I'm coming to. Yes, indeed. Yeah. Okay, so let me look at the gamma 2. This is a logarithmically divergent dimension 4 term. It looks somewhat involved like this. H is that m-dag-rem term. These are some covariant derivatives. You see the little a's here. Everything here is gauge invariant. Okay. Part of this actually looks like f square, but there are other terms, because based on the isometries of CP2, it's not just f square, there are other terms you can make. For example, contraction of FA bar with a metric and square it, that's another possibility. Okay, so there are additional terms possible. So such terms will appear here. But at the end of the day, we had to renormalize it just as we do, and this will end up with a finite coefficient. How do we fix the coefficient? You need some normalization conditions, just as we do in ordinary renormalization. Okay. So, okay, of course, usually in normalization conditions are fixed by BRST symmetry and other requirements. We don't have those things. These are all gauge invariant. There is no BRST here. But nevertheless, there should be some normalization conditions with like the residue of the propagator kind of thing, that kind of stuff. Okay. What about the next term? The gamma 1 is another interesting term. This is quadratically divergent, has a 1 over epsilon behavior. Epsilon is my short distance cutoff square. So 1 over epsilon is quadratic divergence. Okay. But the coefficient here is a little a bar, HA, H inverse. And if I compare with this parametrization, notice that little a occurs here and here. This is quadratic. So this is really a gauge invariant mass term for those degrees of freedom. Okay. It appears with a divergent coefficient. So I have to renormalize this and make it finite. And that's exactly dimensional transmutation in this language. Okay. Because, you know, if you want to define the theory in this, I mean, phrasing it, at least phrasing it as a non-perturbative formulation, then you have to know, you have to define what dimensional transmutation is. And the important thing is that it occurs at the level of the measure of integration, like so. Okay. So in the end, this will end up, the epsilons will disappear, and this will end up with some mass parameter here. This mass parameter, of course, you might say would be related to lambda QCD if you do one loop calculations, and in fact that is the case, and that's what we are, I mean, we are currently checking that. Okay, we can, there is nothing, I haven't lost anything here by this formulation. So in principle, I can recast perturbation theory in this language. So I should be able to do lambda QCD and compare with this to see. Okay, but because this is a mass term, it's going to act as a lower cutoff in terms of various quantities, and which therefore will play the role of lambda QCD. Okay, so there should be some simple numerical relation between M and lambda QCD. Okay. Okay. Is there any evidence for this? I want to.
So why was this not a demonstration of the existence of mass gap?
Because there is another degree of freedom, right? The MM dagger, right? So that is the problem. Okay. So it's very suggestive, but it's not quite there yet. Okay. In the U1, I'm sorry. It's essentially a perpendicular, a transverse square, basically. Yeah, it's roughly speaking that actually. Except, you know, what you mean by transverse is not transverse to K, but transverse in the sense of the CP2 isometries. You have to do that. Okay.
In one case, all this can be carried out, right?
Yeah, except the coefficients in multiplying various terms will be 0, just as in the 2D case. So the mass gap and all these things will arise only because there will be adjoint Casimirs coming in all those expressions. That's where the big difference is, right? So if I do, yeah, I mean, if you look at this, this one here, a lot of terms drop out in the abelian case. You can do a much easier calculation, but you find that there is no term like mass term or anything that arises. Yeah. Okay, I want to show you quickly some evidence for a glue, so to speak, a gluon mass or a massive thing. By looking at the lattice, people have done lattice calculations of some propagator for gluon, so to speak. Okay, it's of course on the lattice the propagator is a difficult question to ask. So one has to talk about it in some gauge or other, but there are this particular one I think is in the Landau gauge. There are different gauges people try to use and get a sense of the propagator on the lattice. And if you do that as a function of q square, that's a momentum square, this is the propagator, and you notice that at low q square it saturates to a finite value. Okay, so that is indicative of the fact that there is a mass in the theory. Okay, so maybe there is some relation there, but I can't say much more about it at this point. The real surprise for me is the last term here. This one, it's a dimension 2 term, which you expect would come with an infinite coefficient, but it comes with a finite coefficient. And that term is a Weissenberg-Witten action. Okay, it's multiplied by c. C is actually related to Casimir's and so on. It's a particular number we can do, and this is again exactly the same as the Weissenberg-Witten action I showed you for 2 dimensions, but upgraded to 4 dimensions by putting the Kähler metric here and the Kähler 2 form here. So this becomes something that is well defined in 4 dimensions. Okay, so this is a 4-dimensional Weissenberg-Witten term action, and that is the term that arises as the leading term in that calculation. Coefficient c is actually finite. It turns out to be this number, where r is the scale factor for CP2. Even if you can also try and do this with an infrared cutoff, so to speak, in which case c is some slightly different value depending on the infrared cutoff, but this is there. Okay. So what does this really mean? That I don't know. I mean, this is the interesting question to ask. Okay. Now, another way to phrase that is, we talked about a mass term for the other degrees of freedom. So coming back to what Chetan was asking, so the 2 transverse degrees of freedom have a mass from here, but then the remaining degrees of freedom that doesn't automatically show a mass gap comes from m and m dagger, that's the h degree of freedom, and that has this contribution. Okay. So if you now consider, for example, a situation where you are below the mass for the transverse degrees of freedom, then essentially the theory is dominated by this Weissenberg-Witten action here. Okay. So therefore there must be some kinematic regime that I can analyze using this, and perhaps there is some interesting physics that one can read off from there. Okay. So I think the 4-dimensional Weissenberg-Witten theory, which of course has a long history, goes back to the work of Donaldson, recent papers by Kevin Costello and so on, and various other people. So you can ask, what are really the degrees of freedom of this 4D Weissenberg-Witten theory, and what is the physics of that? And I don't think that problem is really settled yet. Okay. So it will be very interesting to see what that is, because that would tell us something about the 4-dimensional Young-Mills theory.
So the Weissenberg-Witten structure in +1D case was directly responsible for the mass gap.
That's right. And here also I think there is something like that, but it's 4D, so it's a little hard to pin down. Okay. But on the other hand, it's a very nice action, right? I mean, it's just an upgrading of the Weissenberg-Witten action. So studying it in 4D, we must be able to say something interesting. Okay, the work of Losev et al. Actually talks a little bit about some of the observables, but they are all defined on kind of 2 surfaces and things like that. So it was very hard for me to make sense of it, actually. But I think this problem is, as of now, I believe this is understudied. It has not been investigated sufficiently. So there may be something interesting to see there. Okay. Yeah, I mentioned that there is a Hollecker-Wigman identity for the 4D case also. So one other thing we have is that we can actually use this to calculate the Casimir energy in 4D. Last time I showed you the Casimir energy in 3D and compared with the lattice data. There is a lattice calculation very recently, just last year, done by these guys in 4D, and I'm hoping that I can use this Weissenberg-Witten theory. Where did it go? Here. The Weissenberg-Witten theory here, which are, yeah, basically this theory to get some sense of what the Casimir energy would be. Okay, so that's what I'm going to say about the gauge orbit space, and I mean, we are still working on it. There is some stuff that some more stuff we can talk about, but I want to shift gears and talk a little bit about the infrared issues in QCD, inspired by Alok's talk today morning. Okay, so here is what happens. I mean, we know that if I look at the, say for example, QED, that there is a statement that Lorentz symmetry is spontaneously broken in the non-zero charge sectors of the theory, right? So how does one see that? Can I do a calculation where I simply pick up that part of the physics and focus on it? So I'm not going to discuss all of the subphoton theorems or things of that sort, but here is some simple way to do that. And the action I'm going to use is of this form. So this is just QED. This is the standard action. I'm going to put a lower cutoff on the momenta for lambda. Capital lambda is the UV cutoff of the theory, and it's an exactly similar action with an upper cutoff lambda and lower cutoff mu. This is like the photon mass, if you like, and then there is this extra term. Now where does this come from? This metric here is defined in this fashion with a z naught and a z. This is essentially lapse and shift functions, if you like, on the metric. Eta is the flat metric. So these guys, which are, so to speak, the hard photons, because their momenta exceed lambda, they see this metric, and this is the flat metric, and this is the coupling that arises from z with z and a mu, which appears in here. Okay, this f involves something. This little f is defined in terms of little a. Okay, so this is a separation of scales that I'm doing. The motivation is the following: that if you have a large number of charged particles, net charge is non-zero. Think of it as a big blob of things. Okay, I want to ask, how do I describe the whole dynamics of the whole blob together, coupled to maybe soft photons are there. Okay, so that's like a particle motion in some field of soft photons. That's a part I'm isolating as these two pieces. Okay, notice that if these two pieces are not here, I can eliminate z by a diffeomorphism, and this becomes just standard QED. Okay, so this way of splitting allows me to take care of that, and the z will essentially tell me how this big blob of material moves. Okay, so if you try to do that in 4D, sorry, in nonabelian case, exactly similar structure, except that the coupling now goes through non-trivial charge matrices here, so to speak. But I can represent it in terms of some group element by adding this action, which is the usual co-adjoint orbit action for the gauge group. Okay, so introduce a co-adjoint orbit action, which will give me quantization rules on these charge quantities here, which are defined in the. So U is a group element, and these objects T's are diagonal generators. So this is the charge operator in the theory. And if you quantize the last two pieces here, you basically get nonabelian charge matrices. Okay, so I can use that to couple to the soft photon part, and then this is the remaining part I have. Okay, that would be the nonabelian case. Okay, let's see what one can do with that. So if I take the Hamiltonian, just focusing on, I'm going to ignore the hard part, so to speak, just focus on these three terms. Then the Hamiltonian is basically this. I use small letters because this is just the soft part. This is the coupling between the z's and the a's, and this is the e square and b square. And of course, time evolution would be given by some time ordered exponential like this with the Hamiltonian. Now, here is the important point. We can actually factor out of this Hamiltonian something which means that the time evolution operator, I can factor out an operator here, the same operator at time 0 and a u tilde, where u tilde involves this modified Hamiltonian. Okay. What is going to happen is that the v's will then be identified as dressing factors for the theory. Okay. And so the idea is to seek a solution of this form, which I will explain in more detail. And these functions here, these are just C number quantities, roughly speaking. The hat is the real variable of the theory, and we choose these functions to eliminate interaction terms that may arise when I substitute it here. Okay? So we try to eliminate this interaction term here by choosing V appropriately, and then for the remaining I can simply have normal time evolution by the E square and B square terms. Okay. So if I do that, here is so in the abelian case, here is how it looks. The ansatz I take is like this. Look at H tilde. It has a number of terms, E square plus B square plus all these terms, and you can kill all these terms by choosing these conditions for these functions EC and AC here. Okay, where J of course comes from the current this current dc mu d tau, if you like, or equivalently from this piece here. So if I do that, so I can work out the solution of that. Then you realize that once I have the solution to this problem here, time evolution is now given by U tilde, but it is actually time evolving these dress states like so. Okay. So V therefore defines the dressing factor for the theory. Okay. So what does it look like? Okay, if I write a mode expansion for the still quantum fields in the problem, like so, C and C dagger, then the dress vacuum in the sector with charge q is given by this. This is the coherent state, which is essentially the Kulish-Fadeev thing that you talked about today morning. Okay. So that is simply coming from trying to eliminate the mixing terms in that action. Okay. These omegas are given here, again familiar structure, you have seen this before. These are related to the soft photon factors that one normally encounters. But the important thing is, and here is a nice thing, with this we can explicitly calculate now, take this P, and explicitly calculate the overlap between different values of P and P prime. It takes this form, it's just a bit of calculation. V is the velocity associated with this momentum P. P is a 4 momentum which is dz d tau. Okay. And notice that as mu goes to 0, that's a photon mass goes to 0, this vanishes for any V prime not equal to V. Okay. Even for V prime infinitesimally close to V, which means that the momentum of this blob is superselect. Okay. And this is the violation of Lorentz invariance that people talks about, originally due to Buchholz and Froelich, Morchio and Strokey. Okay. So one can see this explicitly, and this tells us that Lorentz transformations cannot be unitarily implemented. And some years ago, Balachandran and Sachin argued that there is a similar effect for color transformations. Okay. So I want to say a couple of words about that. And
actually, when you put it like this, that if there is a blob, then it's momentum expansion. It might seem odd, but we have seen, one has seen this in other contexts. For example, in heavy quark symmetry.
Exactly. I agree.
Momentum,
Yeah.
the momentum of the particle, momentum of the heavy quark is superselective.
That's right.
And so if one really wants to have an intuitive understanding of Lorentz violation,
Yes.
then that is a good
I agree.
place to pin your
Yes.
intuition.
Exactly. So
Heavy quark symmetry is very well studied and has, has many experimental consequences which have been verified.
right.
So that is a good place to start.
That's right.
to understand,
That's right.
Lorentz violation.
Yeah.
Otherwise, Lorentz violation is makes you very queasy. Makes one
Yeah, yeah.
very
I mean, the way the original papers are phrased,
Yes.
it makes you wonder what is going on, right? I mean, but then when you think of it as this blob, it's much easier to understand. Okay, you want to change the momentum. You got to take this whole thing and move, and you have this infinite soft photon cloud that you have to move, and you can't do that. So it's completely understandable, right? So it's very similar to the heavy quark physics. Yeah.
Is Gurwise.
Yeah, the Isgur-Weiss thing. Yes, that's right. Okay, so let's say a few words about the case with non-zero color. We can do similar analysis, find the dressing factor for color. This is the leading term, and the remaining terms I wrote simply as ik. It's very hard to evaluate. It's a whole infinite series in the case of the nonabelian case. So it's not easy to make statements about it. There is a systematic way to calculate k, which is simply going back to this equation that I showed you. This equation, you take V, ensure that H tilde has no interaction terms with this charge term here. Okay, and because it's non-abelian, of course, it creates an infinite series, but you can systematically do that. Okay, that's true. I didn't do it because I just wanted to focus on this color. Yeah, but you're absolutely right. You could have added, yes. So we take this ansatz and then see what you can do. But if I do just the leading term, I can do the following thing. I construct, so this is the dressing factor coming from here. Now with the nonabelian charge here, now Q, remember, is still an operator because you have to quantize that Kirillov constant action to get the operator structure of Q. So this is still non-trivial to calculate. I do a color rotation and ask, can I get different states S and R for color on both sides? Okay, so this is the, with the dressing, this is the color rotation matrix element that you calculate. If I drop K, I can actually prove that this goes to 0 as the infrared cutoff goes to 0. That means color would be broken. Can I make it as a theorem? Not yet, because we had to show that the K doesn't quite vitiate the result. Okay, so we don't have a good result yet. But the question really is, I mean, given that you can show this, and there is a general argument that color should be broken by the asymptotic considerations involving the essentially the memory operator, basically. It brings back the question, keeping this in mind, how do we define confinement? Okay, confinement is an easy thing to, well, not very easy thing. It's somewhat easy thing to talk about, but defining it is very difficult, right? I mean, the simple definition would be that you calculate the spectrum of the Hamiltonian, all the states of finite energy have no color, no charge. Having said that, though, to implement it in any meaningful way, we talked about the Wilson line. It's not a good diagnostic for this, because there are screenable representations for which the Wilson line just breaks off and flattens out and so on. So there is no really good definition of color confinement that you can practically use. Okay. On top of that, given this possibility that global color rotations are may not be possible, that means that we had to rethink what we mean by confinement and think of how to phrase that. Okay. Of course, this again would not affect calculations we do, things we check against LHC and so on, because everything we do is in a color 0 sector. All the initial hadrons that participate in the collision are colorless. Final states are therefore also colorless. So for that part, this issue may not matter. But as a question of principle, can I have charged states at all in a gauge theory? This would be an issue. Okay. This, of course, this problem doesn't exist for QED. QED may have Lorentz invariance violation, but this problem doesn't exist. It's a purely non-abelian problem. And I think that too needs some resolution before one can say anything more meaningful about it. Okay.
So maybe very naive question. So, but in general, what expects that it will anyway break to the center, right?
That is, well, it's not so much it breaks the center, that to have suggested using that as a diagnostic.
Yeah. Okay. No, I'm saying like I'm not talking about sorry. I'm just saying very naively. If you had like a neutralization type of thing, the current that you get has an E mu, right? If you try to neutralize.
Yeah.
So somehow the fact that these phase transformations don't commute to the mu, does that? I mean, so only that part should anyway be the global symmetric.
Okay, so this goes back to the question of how we implement Gauss's law. So if you give me a theory just purely made of gluons, for example, then the Gauss law can be implemented by saying that the gauge transformations go to a center element at infinity, so that the proper gauge group is actually SU3 mod Z3 or whatever. Yeah, but
Yeah.
but then you can still ask the same
The globe,
same question, right? But also another issue is that if you give me Yang-Mills theory with no quarks or anything, the simplest case, there is no local conserved color current.
What I said is kind of relies on
Yeah.
its existence.
Right. So that is a bit of an issue. I mean, there is some work I'm currently doing on that question, which is how is it related to these edge modes in the theory? The definition of a covariant of a conserved current for color will rely very much on the existence of the edge states. So, I mean, I won't say more at the moment unless there is some question about it. Okay. But anyway, so given that, I'm going to stop here. Thank you very much. I have taken up a lot of your time. Thanks for the opportunity to talk. Okay.
About the part that you talked about in the first half, so is it the Euclidean Yang-Mills?
It's Euclid. I'm looking at Euclidean Yang-Mills, so I can use CP2. If you want to continue straightforwardly to Minkowski, I think the 3-1 signature would be difficult. 2-2 can be done. Okay, but my view is that if I can understand even with Euclidean signature something about confinement, then there should be good lessons that we can take elsewhere. That's the idea, actually.
But there will be some, some one question that one might have is emergence of the four-dimensional term that you get. How sensitive is it to whether you can rotate back to real time?
Okay, it depends. It relies on the existence of the Kähler 2 form.
Yeah.
So 3-1 signature, I can do that, but 2-2 you can do it.
Yeah. No.
Yeah.
But so this is
So
this is in line. It's related to the hope that you expressed that maybe there are lessons for the 3+1 case.
correct, right.
So in
But
particular, one of the important things is the emergence of the.
that's right, right. But you see, a lot of calculations we do in lattice gauge theory is on the presumption that if you calculate a correlation function, and not the action or anything, you calculate some correlation function that can be continued to Minkowski signature, and it essentially retains that, right? That's why we do all these gluon masses calculation. All these things are done by just looking at correlators, right? If you want to think of it in terms of Minkowski signature, it should be a real-time propagator that you are calculating.
But here you are requiring the four manifold to have more than just
That's
first-order Schrader and reflection positivity.
right.
You're requiring it to have a Kähler structure.
That's right.
Whereas lattice people only ask for reflection positivity and.
Right. So what I am hoping is that if I'm able to calculate some correlator here, then I can take a large R limit and then continue that to Minkowski. That's my hope. Okay. So that presumably would work. Okay. There are other ways to think about it also. I mean, for example, I mentioned that CP2 with a conjugation symmetry is like S4. Therefore, if I take certain correlation functions which obey that conjugation symmetry, then those can be easily accepted for S4. And then, of course, you can just take larger limit in a naive way. It should work. Okay. Yeah. So, I mean, there are possible ways to proceed. but I'm not doing any of that now because I think the more important thing is to understand what the Weismann-Witten theory is. Okay. To me, that was a big surprise. I mean, I originally thought it should come with an infinite coefficient. There is nothing.
So maybe I should ask my question. So that part you think will survive the?
I think something of that will survive. Something from there will survive. That's my feeling. Yeah, yeah. And the fact that it's a very different structure from the other terms in the theory. Further, it comes with a finite coefficient, which it had no reason to by dimensional counting. So how did that happen, right? So there is something interesting going on there, actually. Okay. So
if you manage to generalize the, let's say, the 2+1 argument for
mass gap.
From to this
3+1,
sorry, 4-dimensional.
Correct. Yeah.
Then I think at least in this sector, confinement,
mass gap is would be established. That's right. So if one can do that, that will be also really nice, actually. Yeah. So I mean, there is still a lot of things to be sorted out. I'm giving you kind of open-ended things. I mean, I'm not giving you a crisp, nice result at the end. Okay. Yes, definitely. We put scalar fields, because that's easiest to calculate, and it survives.
I think you were saying there is fermions.
Fermions would be a problem. So we didn't put fermions yet, but scalar matter we put, and we calculated. Yes, there is still a Weismann-Witten.
N equals 4 angles, you shouldn't expect.
That's yeah, n equal to 4. Right. Right. Now I showed you last time that this exponential in the 2+1 at least gets progressively cancelled out as you increase the supersymmetry. So maybe something similar would happen here also. Yeah. You had a question.
So just the more general question, which I guess also applies to the lattice space, which is that the Lorentz group here refers because of it's a compact group, right?
Yeah.
So is that the fact that you have by this Euclidean structure, you have compact groups that should use in terms of symmetries of the theory. How relevant is that so finiteness of this term, for example, and so on?
Yeah. So what we did was,
because one of the biggest things that happens is that you go from and I suppose at some level it's also true in the case of lattice calculations, even though you have these theorems that protect you and tell you that the correlation functions are
right.
analytically
Right.
continued to
Yeah.
the Lorentzian case. The fact that this symmetry group changes so drastically, how do you think that would? Because those are kind of the.
I think it will work similar to how it works on the lattice. That's my feeling. Precisely because of that issue, we decided at some point not to use the full-blown CP2, but just use an infrared cutoff. Okay, so that's like taking a smaller portion of CP2 and doing the calculation there. So if you do that infrared cutoff, this term still remains finite, and it is a value given in terms of this lambda. And eventually, if you remove that, that lambda is getting replaced by the radius square of the CP2. So with the infrared cutoff, there is no obstruction to continuing to flat space and getting something that works with Minkowski signature and so on. That's the idea. That's what we hope anyway. Yeah. Okay.
Sorry, but this is section asked earlier. Why do you expect that it should have an infinite permutation?
Because it's a dimension 2 operation, right? So up to dimension 4 should be infinite and then finite. That would be the general expectation. But it's very, very interesting actually that it is not. Okay.
So are there any other questions? So let's thank Parameswaran again. Parameswaran is here till the 2nd. So
Right,
please feel
Friday.
free to catch him and ask him anything and everything you wanted to know about confinement and direct problems, and he will tell you all the answers that he knows.
Oh yeah, which is not a lot, unfortunately.
Well, the answers that he does.